wait for a while. ठीक है, we were discussing this point. Okay, so I hope you have understood the calculation part of VDSB. Then you accordingly calculate. Yes, yes, we need to divide it. Correct. So there will be one more term, that is. So what is that 1.5? Gamma MB. Am I right? Partial safety factor. Great. So by that, I hope you are getting this value of 29 kilonewton. Okay, that is 29. Similarly, you can calculate VDPB. Okay. For VDPB, you will have to assume certain things. Those you are free to assume that, like the pitch distance. Uh, yes, yes. Screen is not visible. Oh, sorry. Wait, wait, wait. Oh, sorry. I hope now it is visible. So this will be gamma MB divided by gamma MB. From that you can get the value to be 29 kilonewton. Then you calculate VDPB value. Now the main part is you need to check, since these bolts will be experiencing, you see, the force in two directions. One is the vertical direction, which is nothing but the shear value that already we have calculated, and then we will be checking the tension capacity of these bolts, isn't it? That is strength of the bolt subjected to tension. For that, we have one formula which is mentioned in this clause number 10.3.5 of your IS code. So you can please refer this, which is on page number 76. What it says, the bolt subjected to factored tensile force TB shall satisfy. TB should be less than or equal to T design B. Okay, tension capacity of the bolt, design tension capacity. What it says, design tension capacity is TNB, that is the nominal tensile capacity of the bolt, which is calculated as this formula. And in this formula, there is one condition which IS code specify. What is that condition? That this 0.9 FUB times AN value, it should be less than FYB times ASB into gamma MB divided by gamma M naught. Okay. So the meaning of this statement or this formula is that whatever may be the least value, that will give you TNB, or that you should take or you should consider to be TNB. Okay. So let us go step by step and find out TDB. TDB यानी TNB divided by gamma MB. So this numerator part actually is TNB. Okay. So we need to identify whether this TNB is as per the formula or as per the check which is specified by the IS code. So what, how much will be the value based on this formula? 0.9 times FUB times ANB. So what is this FUB value? How much should be the value? Yes, 400. A and B. For A and B or for AN, as per this formula, what it says, net tensile stress area as specified in the appropriate Indian standard. For bolts where the tensile stress area is not defined, AN shall be taken as the area at the bottom of the threads. At the bottom of the threads. That is nothing but your 0.78 times area of the bolt. ठीक है, वो कितना आता है देखो, 0.78 times area of the bolt. What is the area mentioned? Rather, what is the diameter of the bolt given? 16 mm. So, can you please find out this complete value? 0.9 into 400 into 0.78 times pi d square by 4. D stands for the diameter of the bolt. And just let me know whether you are getting this value or not. फोर फाइव ठीक है 56.45 and what about this on the right hand side you can see FYB into ASB into gamma MB divided by gamma M naught. So gamma MB we know what is the value of gamma MB 1 point and what about gamma M naught that you will have to check in the IS code. What is that table number? Table 5, am I right? So please check and please substitute the proper value in this equation. As per the information, it is 1.1. Okay. Then what is this FYB? FYB is the yield stress of the bolt. From where will you get this yield stress of the bolt? Again from IS code. Okay. So can you verify the FYB value? कितना रहेगा? For 4.6 grade, what should be the FYB value? चलो बताओ. We have discussed this thing, if you remember. Do you remember this thing? Yes. Or else what you can do is, if you don't remember, there is no problem as such. What else you can do is, you can refer IS code. In the IS code, you will see your table 1, page number 14, rather 13. Okay. Table number 1. This tensile properties of the structural steel products. Over here, can you see for 4.6 grade, do you observe any kind of yield stress value? Only ultimate tensile stress value is given. Yield stress value is not given. But if you remember, I had told you that to calculate the yield stress value, the significance of this 4.6 grade, what does 4 stands for? 4 is nothing but 1/100th of the yield stress value, and 0.6 is nothing but the ratio of the you can say ultimate tensile stress to the yield stress value. By this, how much value should be the I mean how much should be the value for yield stress? It will be nothing but 400 into 0.6, that is 240. Okay, and therefore over here you will see, over here the value of FYB, it comes out to be 240 MPa. Okay, what is ASB? ASB is shank area of the bolt. That is nothing but the area of the bolt diameter, you can say. That is pi d square by 4. With this, please check whatever value I have calculated whether this is okay. 54, I am getting 54.82. करेक्ट है क्या, देख लो एक बार. Are you getting this value? 54.83. ठीक है. So this value, this is not, I mean this left hand side is not less than right hand side, and therefore we cannot make use of this equation. As per IS code, we need to consider this because this is the least value. Uh, this should be the value which has to be checked, and if this value doesn't come out to be less than this, then you are supposed to consider the least value. Okay, so over here TNB shall be 54.82. अगर ये इससे लेस आता है तो हमको ये कंसिडर करना है, but in this case since it is more, we need to substitute the proper value. Have you understood this thing? Therefore TDB will be TNB divided by gamma MB. Okay, so this is how the tension capacity of the bolt is to be calculated. Got it? Then we need to actually confirm whether that whether those bolts which are provided in section 11 they are safe in shear. First of all, we have found that. Secondly, whether they are safe in tension or not. So first step is what we have calculated the tension capacity. Now the second step is to calculate this part, that is shear in each bolt. Shear in each bolt is calculated as factored vertical force component divided by number of bolts, and second is the tension in each bolt, which is given by factored horizontal force component by number of bolts. So total number of bolts are 8. We have also calculated the factored vertical force component and in the earlier stage itself. Based on that, we will be calculating the total shear in each bolt. This comes out to be 17.68. Similarly, we are calculating total tension in each bolt. This will again be the same because the angle of inclination is 45 degree. Okay, this we are finding out in order to check this interaction formula. And what it says, bolt subjected to combined shear and tension should be less than or equal to 1. And as per this formula, it says VSB divided by VDB plus TB divided by TDB whole square should be less than or equal to 1. So the denominator values we have already evaluated, as you can see over here, VDSB and the TDB values. The numerator values were remaining, and these numerator values can be evaluated by this formulation. It is very simple, right? Then you substitute the value and you will find that the value is less than or equal to 1. And therefore we can say now that the complete section 11 bolts, they are safe in combined effect of tension and shear. Okay, this you can find on page number again 76. Clause is 10.3.6 in your IS 800 2007. Okay? So this is how we are supposed to check the capacity of the bolts when they are subjected to two effects. So the combined effect has to be verified. So IS code has provided this formula. You just have to calculate the essential parameters, substitute them and check it. Okay? Next step is to identify the number of bolts for this section. Got it? So let's go for that. Strength of the bolt in double shear. We know that this portion will experience double shear and bearing as we have discussed earlier. Okay? So what you do, you calculate VDSB, and while calculating VDSB, you are supposed to take care that since it is in double shear, that value will be multiplied by 2. Similarly, strength of the bolt in bearing, that has to be calculated, and while calculating, please make sure that this T value should be the least value. तो मुझे एक चीज बताओ. I have left that portion for you people to solve. Just let me know out of this which one will be the least value that I will have to consider in that BDPB equation. See, this is 8 mm, this is 8 mm. What is the thickness of the web plate? It is 10 mm thick. अब बताओ, what T value should I place? 10. Great, it will be 10 mm. So I think you have understood, you have visualized the bearing stresses in front of your eyes, and based on that you have told me that this will be the 10 mm thickness value. That is correct. So from that you can identify the number of bolts those will be required, and that will be nothing but factor load divided by minimum of shear and bearing. ठीक है? So remember one thing, ये जो number of bolts हमने calculate किए है इस numerical के लिए, we don't have right now the background related to few more parameters, because the calculation of number of bolts will be actually calculated based on few more things. Okay, and you will see that minimum of in bracket value, those will not be just restricted to shear and bearing, those may be some other values also. But for for initial understanding and with limited knowledge, we can definitely calculate the number of bolts depending on these two parameters. Okay, so therefore I have written one note over here. Okay, whether this complete section is safe in various parameters, I will be discussing it in the coming lectures. However, without these checks, no design is complete, because what you can say, you have identified the number of bolts. After that, whether the section is whatever number of bolts you are providing to that section, whether that section will remain safe or not, that has to be checked, and those check will be discussed in the coming lectures. Okay, so I hope you have understood this thing. You are supposed to calculate the number of bolts. This is a kind of homework, you can say. You can solve this. Okay, now what I am trying to say is about these checks and the design aspect. For that you need to understand few things. I will just begin the introduction part, and then I will stop. See, first member which we will be dealing with after the discussion of the capacity of the bolt, capacity of the plate. Now we will see what type of different types of members are available in steel structure. First is the tension member. Very simple, tension members are linear members in which axial forces act so as to elongate or stretch the member. It is as simple as that. They carry the loads most efficiently since the entire cross section is subjected to uniform stresses. So common example for tension members may be the rafter of the roof truss, tie member. Then as far as the bridge is concerned, these are the cable stay cables or the stayed bridge, wherein these cables will experience tension force. Also, these are the suspenders of the bridge which will be experiencing the tension force. Okay, then the building which is commonly known as suspended building. Over here, these are the suspenders, they experience the tension force. Then there are a few components like the sag rod, purlin, all these things I will be discussing when we will cover the industrial roof analysis. In that case, you will come across this sag rod and purlin concept, right? So all these members, they experience tension force. These bracings in the building frame, that may also experience tension force. So these are the typical tension members which you may come across. Typical cross section of the tension members, as you can see, the angle section. This is the double angle section most commonly used when the capacity of the member it increases, and when we are supposed to design or take care of huge capacity. In that case, we provide such kind of double angle sections. Then the channel section, then this is known as built up section. Built up in the sense that there are two channel sections, as you can see over here. They are connected to each other with the help of this plate arrangement. Okay, so they are known as built up sections. There may be I section, built up I section, then cable. These are tendons, pre-stressing cables, you can say. Okay, there are different modes of failure associated to the tension members, and based on, remember, I will not go into the detail right now. Just remember this thing, that these modes of failure, they are essential in order to decide the overall dimension of the connection. It may be the number of bolts, it may be the complete dimension of the plate. Depending on these modes of failure, you are supposed to design the connection. Okay, so very broadly, there are three modes of failures, which is gross section yielding, net section rupture. Okay, net section rupture and block shear failure. These are the three modes of failure associated to the tension member. And you will see, based on these three concepts or these three modes, the complete design revolves around. So initial numerical, whatever we have seen, those were just a you can say introduction, just a part of the complete picture. It was just a introductory part. But now you will slowly come to understand that how to make use of these three modes of failure in order to make your connection stable, in order to check whether the connection is safe or not. Okay? So I will be discussing these three concepts in the coming lectures, and later on we will see how to design a tension member or any member with respect to these three checks. Okay, so I will stop over here, and I will be distributing, or I will be uploading the notes today, the notes pertaining to the initial part of our discussion. And whatever right now, this PPT, whatever I am explaining, I will be giving it to you later on, but the previous notes I will be uploading on the classroom by today. Okay, so so thank you very much. I will leave. You people also should leave. Thank you.